Our title or project is called Photonic Switch Model for Data Application. My name is Saul Davis. I'm a mechanical engineering major. I'm attending San Diego City College. This is my colleague.
Victor Sandoval, Aerospace Engineering from San Diego City College.
Victor Rojas, Electrical Engineering from Santa Barbara City College.
I'm Diego Campos, also from Santa Barbara City College, and I'm studying electrical engineering. Our mentor was Luis Chan and Devin McCarthy, and we got the opportunity to work on the Diego Rajan research group. So, have you ever thought of what happens when you search something using the internet? I will say an example. Let's say you want to do your research about dogs. So you go to Google and type dog, and you find a page with a lot of links. You start clicking on the links until you find information you want. But you never think about how many data you're using, how much energy you're consuming, or how much CO2 you're emitting. What about 7 billion people in the world and about 2 billion people have internet access? That means like a lot of people do what I just did in my example. Every time you use a computer, you're wasting two things, energy and memory. What happens is that you need energy to keep your computer working. But you never realize what happened with all the data you use on the internet. That data needs to be stored in some place. That place is called a data center. A data center is a place with a lot of computers. In all these computers, we store all the information from sites such as Facebook or Google. We transfer the data from your computer to these data centers using switches. Actually, we have in the world about 500,000 data centers with about 1.3 trillion gigabytes of information. This is costing the world about $426 billion each year. Because these data centers have all switch technology, they need a lot of energy to work. This energy is mainly electricity. This electricity is produced by burning coal. This coal produces a lot of CO2, and later it's going to affect us. In 2007, 80 metric megatons of CO2 were produced to keep all the world data centers working. And it is projected that in 2020, this number is going to rise to 340 metric megatons of CO2. In this table, we're comparing 3 countries and all the CO2 they produce each year. If we keep rising this number, we're going to need more CO2 to keep these data centers working than the total emission of these countries.
With that said, switches, how they work. Switch give direction and control the flow. One example, traffic lights. Traffic lights control the traffic and give direction for the driver. Optical switch is the same thing as an atomic switch, but they use light. By saying that, the switch usually has high speed performance and has a lot of storage to store the data. And what's so unique about this switch is uses very, very low power, meaning that it can be helpful for our environment, so we can use for our data centers. Our goal is to design and build a model of a switch. Since the optical switch is so expensive, then we use a cheaper model of a chip. We will use a software and design and simulate our switch. And we will create a physical model, and by testing it, we use audio. For materials, we use a power supply that gives voltage, and we use a breadboard that's a platform for a circuit board. A function generator gives waves, and the oscilloscope will be able to read that. And multimeter will be using for testing the voltage, and we're using the chip.
Now here's a system of how our whole setup works. We have the power supply that gives the voltage inside there, which helps the current go through. The function generator gives a wave that will collaborate with the voltage and go through our circuits. From there, we will test the wave frequency using our oscillator to make sure we have the right frequency on the board. After that, we will check a multimeter and check if the voltages are right and make sure that our switch is working properly. When that is all made sure of, we will now connect it to the audio, and if we hear music coming out the other side that we plugged in through one, it means that our switch has been composed properly. To make this whole system work, it all has to go through the breadboard and through our system, which is made of chips. Now, a chip is made of multiplexers. A multiplexer is made out of 2 inputs, 1 selector, and 1 output. And see, as you can see here, these are 2 entrances that have the 0 and the 1. If the select is 0, the input next to the 1, the entrance of the 0, will be output, the output. If the select is 1, the input next to the entrance of 1 will now be the output. And now when these 2 multiplexers when we have 2 multiplexers, they make a system. And that system is a 2x2 switch or a chip. Now these chips have 2 stages. Stage of bar, or bar stage, and a cross stage. When the select is 0, it has a bar stage, and it just means that the current and the waves will just go right across it. If it has a select 1, it will be a cross stage, meaning it will be diagonal. The A will cross diagonally down, and the B will cross diagonally up. And now all these chips we compose out of 6 to make our 4x4 switch, which is this, meaning it has 4 inputs and 4 outputs. We input data, and we can manipulate what output we want it to come out by changing the selectors on each chip. That will help us sort of get it through our circuit and into the audio.
So when we started building our circuit, we wanted to test the voltage because we don't want to, complete the whole circuit and then, have to find the problems. So we had to test each multiplexer. And to remind you again, this is a multiplexer. The way it works is a selector will read 0s and 1s because it's a digital device. And so basically, if the select is 0, the input on 0 will come out. If the selector is 1, the input next to 1 will come out. As you can see in our data table, when the voltage is low on A and the selector is low, the A input is going to come out, which we put a low input and we got a low output. When we made the selector, again, a 0, we put a high voltage on A and we got a high voltage as the output. A low voltage can be anywhere between 0 to 0.2 voltages. High voltage can be anywhere between 4 to 6. So after we were able to build our circuit, first of all, we were very excited because I had never done this before. So we wanted to test it by using audio. The way it worked was we got music from our laptop. It was converted from, the music from the laptop is an analog signal. It was converted into digital. It went through our circuit, this one here, and then it was converted back into analog, which then went to the speaker and it emitted audio. In conclusion, we were able to simulate our optical switch by building on a circuit. We were also able to physically build it, and we were able to test it by using audio. There were some times when we weren't getting an audio on the other side, so we had to repeat, just make sure that all the connections were connected properly. And we just wanted to thank the Cooke Bridges program, all the staff, Ofelia Aguirre, Jens, Kuhn, all the RAs, thank you for your support and your guidance. Our mentor, Luis Chen, is here, thank you for being here. And all the people from the Rajan Research Group and our family and audience. All of our parents, thank you for being here. Thank you.